We need to be able to relate this binomial distribution to real life examples, and the reason why the binomial distribution has a special name for those types of random variables is because the binomial distribution comes up in a lot of real life situations. So here we've got a sample of 20 people, and the probability that a random member of the group is left-handed is 0.15. And we're going to count how many people are left-handed from this sample. So we've got 20, you can kind of think about this as 20 trials, where each trial is we ask one person whether they're left-handed or not. And each person is either left-handed or not left-handed. So the 20 trials are the 20 members, and here success is going to be left-handed because we're counting how many successes we have, how many left-handed people we have. So let's say that we're doing 20 trials, i.e. asking 20 people. Each trial is either, well, each person is going to either be left-handed, and because we're counting the number of left-handed people, we're going to say that that's a success. And or they could be right-handed. And because we're not counting the number of right-handed people, that would be what we've called failure up until now. So we can say that X is going to follow a binomial distribution. And we're doing 20 trials, so N is 20. And the probability of success is the probability of someone being left-handed because we're counting the number of left-handed people, which is 0.15. So P equals 0.15. So this is our model, binomial 20, 0.15. And remember, you could also write that as X follows a binomial 20, 0.15. And all this does is it tells us that we know what the probability distribution is. So for a given value of X, we can use the formula that we've learned to work out what the probability of having that number of left-handed people is. So use your model to calculate the probability that exactly 7 of the members in the sample are left-handed. So this is basically asking us what's the probability that X, the number of left-handed people, is equal to 7. So we're going to use the formula n choose X, P to the power of X, 1 minus P to the power of n minus X. So n is 20. Here, X, our specific X value, is 7. So this basically tells us that little x is 7. And then we're going to have P, which is 0.15 to the power of 7, and 1 minus P to the power of 20 minus 7. So we can write that as 20 choose 7 times 0.15 to the power of 7 times 0.85 to the power of 13. And notice that the powers add up to 20, and one of the power, what we're choosing matches how many successes we've got. And remember, in a previous video, we said this is because we're going to go down, if we drew a tree diagram, we're going to go down 7 branches where they have to be left-handed probabilities, and we're going to go down 13 branches where the probability is right-handed. That's the right-handed probability. And this choose function at the start tells us how many different ways are there of choosing 7 people who are going to be left-handed out of the 20. And we can work out what that probability is. 0.0160 to 3 sig fig. And in part 2, we're asked for fewer than 2 of the members in the sample being left-handed. So we always try and relate it to the binomial distribution. That's the same as saying X, the number of left-handed people, is going to be less than 2. So if we think, what does X need to be equal to for it to be less than 2? Well, x could either be 0 or x could be 1. And because it's that one or that one, we need to add these two probabilities together. So let's write down the probability of x being 0. So that's 20 choose 0 times 0.15 to the power of 0 times 0.85 to the power of 20, and plus 20 choose 1 times 0.15 to the power of 1 times 0.85 to the power of 19. And we can work out what that probability is. And we get 0.176 to 3 sig fig. So hopefully you can see that it's a lot easier than having to draw out a massive tree diagram. Just using this formula saves us a lot of time.